Okay, in this unit we're dealing with gas laws. We've been talking a lot about gases and particles and what's happening on the main scale without actually talking about calculations that we can do, but we always want to think about what is it that's happening on the particle level as we're dealing with gases. So here's a question to start us off. If you increase the temperature of a gas and maintain constant pressure, so we're not changing the pressure that's on the gas at all, and it's not changing as a result, we're wondering what's going to happen to the volume of the gas. So let's say I've got a balloon and I'm increasing the temperature of the gas particles in the balloon. Maybe I have a hair dryer and I'm heating up that gas. Well, we know that temperature is related to kinetic energy, and so if I'm heating up the gas, my temperature is increasing as well as the speed of the particles is increasing. So they're moving around a whole lot more. So my balloon is going to get bigger. The volume is going to get bigger because the more that they are moving around, the more that they're going to push each other out, and the more that the volume is going to increase to keep that pressure the same. And so that's D increases because the particles are moving more quickly. So in gas laws, there's a few things that we need to know right off the bat, and so we're going to write this right at the top of our notes so that we don't forget them. So first of all, we need to realize that any temperature in gas laws must be in the unit of kelvins. The reason that it must be in the unit of kelvins is because anything that's in Celsius or Fahrenheit has the potential of being negative. And if we're having negative temperatures, we could potentially get values for our pressures and volumes that are negative. And we can't have negative pressures and volumes, so that means that our temperature scale is always using Kelvin. The Kelvin temperature scale goes from 0 to really high numbers, so no negative numbers are involved with Kelvin. And the way that we're going to get to Kelvin, and Kelvin's just with a big capital K, and that's what I've got here, my temperature in kelvins is equal to whatever my temperature reads in Celsius. That's what we're probably going to see in our classroom, is Celsius in temperature. But then we add 273 to it. So let's take freezing water. Freezing water is 0 degrees Celsius. That means that my temperature of that 0 degrees Celsius is actually 273 Kelvin. So freezing water has a temperature of 273 kelvins. So that's a good one to know, and remember that we always need to make sure that our temperature in gas laws is converted to kelvins if it's not already in kelvins. We also need to know that 1 liter is the same thing as 1 decimeters cubed. Those are both volume measurements, units for volume, and 1 liter is the same thing as a decimeter cubed. You probably also remember that there's 1,000 milliliters in every liter. So that means that there's 1,000 milliliters in 1 decimeters cubed. We also are going to run into this unit. This is a new unit for us, and it's a unit for pressure, because gases are all dealing with temperature, volumes, and pressures. So for pressure, a kPa, notice that this is a lowercase k, capital P, lowercase a. That stands for kilopascals. And that's just, Pascals is a guy that used to be a science guy. And so they named this unit after him because he's done a lot. And then kilo is just the unit of it. Sometimes you'll see things in pascals, and there's 1,000 pascals for every kilopascal, just like a normal base unit would be for kilo. Okay, so we're going to take a little sidetrack for a moment to figure out what the mole is, because the mole is going to come in handy for us when we're dealing with gas laws. So moles, as an introduction, first we want to think about dozen. Okay, if I say a dozen of something, I have a dozen of something. Well, we're talking about 12. Like a dozen eggs is 12 eggs. Sometimes we say, though, that we have a mole of something. And the reason we use this number mole is because this is a lot of things. 6.02 times 10 to the 23 things, or 602 with 21 zeros behind it. That's 1 mole. 1 mole is a heck of a lot easier to deal with than 6.02 times 10 to the 23. We want it to be even more easy than that. We want to know what 1 mole is in some sort of unit that I can measure. And this is all based on the periodic table. So the moles of an atom is equal to the mass in grams from the periodic table. So the molar mass on the periodic table, so let's look at carbon. Carbon has a molar mass of 12.01. So that means for every mole of carbon I have on the scale a mass of 12.01 grams. So we can look at the periodic table again and figure out the mass of 1 mole of oxygen. Well, oxygen I see is roughly 16 grams per mole. And there's 2 oxygens there. That's what that little subscript 2 means. There's 2 oxygens. So I really have 2 times 16. 2 of my masses of 16, which is 32 grams. That's 1 mole. Now I want to know how many moles are in 64 grams of O2. So I'm still using O2, and I know that the molar mass of 1 mole of O2 is 32 grams. So if I measured out 64 grams, if I had a way of measuring out mass of a gas on a scale and measured out 64 grams, how many moles would that be? Well, it would be 64 divided by 32. That'd be 2 moles. And there you guys go. You just did a little bit of stoichiometry. A big scary word that some people are like, oh my goodness, it's stoichiometry. It's not that tough. We just did some stoichiometry and we haven't even gotten to that unit this year. So why did we take that diversion about moles? Well, moles show up in number of particles within our gas laws. And Avogadros, the guy that came up with the 6.02 times 10 to the 23 to start with, but he also came up something with that applied to gases specifically. And it's the amount of gas is equal to the volume of the container that you have your gas in divided by molar volume. Now the confusing part is, what is molar volume? Well, molar volume is a constant. It's 22.7 decimeters cubed per mole at standard temperature and pressure. So this is a new notation for us. IB really likes to put their units this way, where they put a negative number. Maybe it's a -2, maybe it's a -4. What that means is that this is on my denominator of my fraction. So my unit, it's a combined unit, is decimeters cubed divided by moles to 1. Okay, and we don't have to write it out. Decimeters cubed per mole is my molar volume. And standard temperature and pressure, STP, has pressure of 1 atmosphere, which is the same as 100 kilopascals, and a temperature of 273 kelvins. Now, the big question is, do I have to memorize all of that? Well, lucky for us, we have a data booklet on all of our tests, and the molar volume of an ideal gas at standard temperature and pressure is given to us in that data booklet. We also have the STP conditions given to us in the data booklet, along with a bunch of other stuff. So I need to know where to find my information, but at least I know that it exists. It's there. I don't have to memorize it. Now, continuing on with Avogadros Lie, he wanted to see if there was a relationship between the number of moles and the volume if you have changes in either volume or moles. So what he came up with was that if the temperature and the pressure of the gas are held constant, the volume, or V, and the number of moles, which we represent with N, are directly proportional. So the question is, what does directly proportional mean? Well, it means that if I increase the number of moles that I have, they're going to take up a bigger volume. So if I shoot moles into my container, it's going to have a bigger volume. So if I decrease them, then it's going to have a decreased volume. If I took some out, it would be a decreased volume. The 1 stands for initial conditions, the 2 stands for final conditions, and that is where we are going to stop for our first set of notes.